So this is the critical statement of the central limit theorem that we're going to be using a fair bit. So first of all, the sum of values is the random variable Sn, which is equal to x1 plus x2 plus x3 plus and all the way up to plus xn. That's the notation we use. And the mean of the values is the random variable x bar n, which is x1 plus x2 plus x3, added all the way up to xn, and it's that divided by n. That's the notation we can use for distribution of means. Now, we both are called sampling distributions. So, the key theorem says that if many sufficiently large random samples are taken from a population of any shape, so the population distribution can be any shape, it can be skewed, it can be normal, or it can be something entirely different, then the distribution of the sum of the samples, Sn, and of the sample means, x bar n, is approximately normal. So that's what we saw last time. So for a sample of size n, the mean of the sums, which you call mu of Sn, mu of Sn is the mean of the sums, is actually equal to the sample size times mu of x. In other words, that's the mean of our original distribution. And the standard deviation of the sums, which we can say is sigma of Sn, is equal to the square root of n, the square root of the sample times square root of the sample size times sigma, where this sigma is the standard deviation of x, where x again is our original distribution. So we'll see that going from the original distribution x to the standard deviation of s of n is actually going to mean our standard deviation increases. And just to make it clear, that's a time sign, so I'll make it a dot. Now the mean of the means, mu of x bar of n, is constant and is equal to the population mean. Standard deviations of means, we saw from the graph that actually goes down, which means that sigma of x bar of n is actually going to be sigma over the square root of n. So in this case, for the means, we divide by the square root of n. For the sums, we multiply by the square root of n. And as n increases, we've already seen that the approximation to normality improves, gets better. It's going to be more normal the larger the sample size. and the standard deviations of sums. So this is as n increases, the standard deviations of sums, which is sigma of Sn, is going to increase, but the standard deviations of means, sigma of x bar of n, is going to decrease. But this doesn't really answer the big question, which is how large should n be before we can say that the central limit theorem can be applied. Like if we've got a distribution, how large does n actually have to be so we can say we've got a normal distribution? So we can say the sums or the means is actually a normal distribution. And there's no simple answer to that. It's going to depend on a lot of things. So if the population is skewed, it could require quite a large sample size. Whereas if the population is symmetric, then maybe we only need a small sample size to be able to get something that's normal. However, we can say something specific. So in the special case where the population is normally distributed originally, so the original distribution is normal, then the distribution of the means and the distributions of the sums is always normal. In other words, it will be normal for any sample size. No sample size is going to be not normal. So if the original distribution is normally distributed, then the distribution of means and sums will always be normal. We can guarantee that for any sample size. So we can actually say, we can apply the central limit theorem to small samples if we know that x bar for a smaller sample is already normal, or in the special case where the population is normally distributed. Then we can say the distribution of x bar is normally distributed. And this also applies to the distributions of sums as well. So just to explain the top point, if we say got a sample size of 5 and they show us the distribution of the means or the sums for a sample of 5, and we can see that that's close enough to be approximately normal, then we know that everything above it is going to be approximately normal as well. Because as the sample size increases, the approximation to normality is only going to get better, it's not going to get worse. So if we take a distribution from a smaller sample and that's normal, then we can say everything above it is normal. And also in the case where the population is normally distributed, then the distribution is going to be of the means and the sums is normal as well. Now, remember that when we're using the central limit theorem, we're concerned with the distribution of sample sums and means. We are not concerned with the distribution of individual scores, which is the original distribution.